Hi folks, this video covers section 3.8 of the textbook, Exponential Growth and Decay. So today we're going to see three examples of application of differentiation. The first one is population growth, the second one radioactive decay, and the third one is Newton's law of cooling. So let's suppose that we are regarding a population P as only depending on its birth and death rates. So dp over dt is going to be the variation of the population over time, is going to be given by the birth rate minus the death rate. In the problems that we are going to see, we are always going to assume that the birth and death rates, they are proportional to the current size of the population. And being proportional to the size of the population means that they are simply a multiplication of the population by a constant. So the birth rate is going to be K1 times P, and the death rate is going to be K2 times P. Well, in this expression, we can factor P, and we're going to have P times K1 minus K2. And instead of dealing with two constants, we deal with only one constant, and we call it K. So this is going to give us the mathematical model dp over dt is equal to kp, where p of 0 is equal to p0. So p of 0 means the population at time 0. It's just another way of saying the initial population. So this model is called the Malthusian model of population. And then we have this differential equation, dp over dt is equal to kp, where p0 is equal to p of 0, the initial population. So a differential equation is an equation that relates a function with its derivative. So here we have a function p. So keep in mind that p is a function p of t. And dp dt is the same thing as p prime. So this equation here, it relates a function p with its derivative. So it's called a differential equation. So our claim is that this kind of differential equation only has one solution, given by p of t equals p of 0, the initial population, times e raised to kt. Well, to see that this is true, what we do is we take the derivative of p of t. So let's take the derivative of that. So we're going to have dp dt is going to be equal to d dt of p0 e raised to kt. Well, on the right-hand side, p0 is the initial population, so it's a constant. So we keep the constant. Now here we have exponential raised to, we have e raised to k times t. So by the chain rule, the derivative of that is e raised to kt times the derivative of the inner function. Kt is the inner function. So we have to multiply by k. So indeed, we have that dp over dt is equal to k times p0 times e raised to kt. And if we replace p0 e to kt by t, by p of t, we're going to have k times p of t. So indeed, dp over dt is equal to kp, like we claimed initially. So it does satisfy the differential equation. Well, if the birth rate is higher than the death rate, it means that K1 is going to be bigger than K2. So remember from the previous slide that K1 and K2 were the constants that the birth and death rates were proportional to. And in this case, K is going to be bigger than 0. So this model In this case, is going to give a growth, is going to be a growth model. If the birth rate is lower than the death rate, then K1 is going to be less than K2, which is going to imply that K is less than 0. And in this case, P of T is going to be called a decay model. But in both cases, the constant K is going to be called the relative growth rate because it can be obtained by dividing dp/dt by P. So let's consider this example. A bacteria culture initially contains 100 cells and it grows at a rate proportional to its size. After half an hour, the population has increased to 500. So in letter A, we are asked to find the relative growth rate, which is the K in our formula from the previous slide. In letter B, we have to find an expression for the number of bacteria after T hours. So in other words, we want to give a function of the population of bacteria, so the bacteria culture, the number of cells at a given time T. And in letter C, they ask when will the population reach 10,000 cells? So we're saying that P of T is going to be at some point equal to 10,000. And then this implies that T is equal to what? That's what we are asking in letter C. So let's interpret this problem. It's saying that the bacteria culture is growing at a rate that is proportional to its size. So um, the population is growing at a rate that is proportional to its size. So dp/dt is equal to K times P. And then like we saw, this kind of differential equation, it has a solution, it has as only solution P of T equals P0, the initial population, times e raised to K times T. We are told that initially the bacteria culture contains 100 cells, so P0 or P of 0, that is equal to 100 cells. And we are also told that after half an hour, the population has increased to 500. So P of half is equal to 500. We are going to combine this information with this one. So we're going to plug T equals half and P of T equals 500 in this equation here. And let's see what we get. So 500 is going to be equal to P0. Well, P0 is the initial population. We're told that it's 100 times E raised to K times T. Well, T is equal to half. So this is going to be K over 2. So we're going to divide both sides by 100. So we have E raised to K over 2 is equal to 5. So to find K, which is what we are asked in part A, we have to take ln on both sides. So ln of E to K over 2 is equal to ln of 5. So ln and exponential are inverse functions of each other. So on the left-hand side, we have K over 2. And on the right-hand side, we have ln of 5. So K is going to be equal to 2 times ln of 5. So we replace that into this equation here. So P of T is going to be equal to P0, while the initial population is 100, times E raised to K, which is 2 ln 5, times T. So this expression here, it gives the number of bacteria after T hours. So that is P of T. which is the answer to part B. So here we have the same information but typed. So finally, let's solve part C. When will the population reach 10,000 cells? So in other words, uh, sorry, not P of 10,000. So P of T is gonna be 10,000, implies that T is equal to what? So we had the formula from the previous slide, that P of T was equal to 100, the initial population, times E raised to K, which we found was equal to 2 ln 5 times T. So we have to find the value of T that makes P of T equal to 10,000. So 10,000 equals 100 times E raised to T 2 ln 5. We're going to divide both sides by 100. So we have E raised to T 2 ln 5 equals 100. So now we are going to take ln on both sides. And because E and ln are inverse functions of each other, on the left-hand side, we're going to have T times 2 ln 5. And on the right-hand side, we're going to have ln 100. So finally, solving for T gives us ln of 100 over 2 ln 5. And to solve this last step, you would need a calculator to find approximately 1.4 hours. So the population is going to reach 10,000 of cells after 1.4 hours, which is what we have here in this slide. In our previous example, we were using the model P of T equals P0, the initial population, times E raised to K times T. So P of T represented the population at a given time T, and P0 represented the initial population. It turns out that the population can be interpreted very loosely. So a population can be the number of people, the number of animals, the number of bacteria, as we saw in the previous example, or even atoms. So in the last case, uh, typically the population is in decay. So there is empirical evidence that supports that the mass of a radioactive substance varies according to the same model that we were using. So in our previous model, we had P of T and P0. So in our new examples of radioactive decay, P0 is going to be replaced by M0, the initial mass of the substance, and P of T is going to be replaced by M of T, which is the mass of the substance at a given time T. Let's consider this example where we have a sample of a radioactive substance that decayed to 91% of its original amount after 1 year. Then we have to find the half-life of the substance and also at what percentage of the substance would remain after a century. So our model now is M of T equals M0, the initial mass, times E raised to KT. So first, we are asked about the half-life of the substance. In other words, we are asking the amount of time that it takes for the substance to decay to 50% of its original amount. So representing this mathematically, we have M of T is going to be 50% or 0.5 times the initial amount of substance. So 0.5 times M0. And we want to find the value of T that satisfies this, that satisfies m of t equals to 0.5 m0. That is what half-life of a substance is. We are told that the substance decayed to 91% of its original amount after a year. So it means that m of 1, so after 1 year, we had uh, 0.91 times the original mass, which is m0. So we're going to combine those two pieces of information, and we are going to plug t equals 1 in this equation. So we have m of 1, which is 0.921 m0. That is going to be equal to m0 times e raised to k times t, but we are plugging t equals 1. So it's going to be simply e raised to k. Well, we can um, divide both sides by m0, and we're going to get e raised to k is equal to 0.91. So taking ln on both sides, this is going to give us on the left k, and on the right ln of 0.91. We found k, so we can replace in this equation to give the mass of the substance at a time t. It's going to be equal to the original, the initial mass, m0, times e raised to k, which is ln of 0.91, times t. So what we are asking is m of t is equal to 0.5 times m0 for what value of t. So we are going to combine those two equations. So we're going to replace m of t in the first equation by 0.5 times m0. So this gives us 0.5 m0 equals m0 e raised to ln of 0.91 times t. We can cancel this m0 with this m0. So we have on the right e raised to t ln of 0.91 is going to be equal to 0.5. We can take ln on both sides, and because ln and exponential are inverse functions of each other, on the left we're going to have t times ln of 0.91, and on the right we're going to have ln of 0.5. So let's divide both sides by ln of 0.91. This is going to be ln of 0.5 divided by ln of 0.91. And at this point, you would need a calculator to find the answer, which is approximately 7.35 years. So let's see the part B. What percentage of the substance would remain after a century? Even though we already have the answer here, let me explain in a different way than what is written. We have that m of t is equal to m0 times e raised to k, which is ln of 0.91 times t. So they are asking what percentage of the substance would remain after a century. In other words, m of 100 is equal to what? It's going to be m0 times e raised to 100 times ln of 0.91. So m0, not m0, m of 100 is going to be equal to m0 times, well, we are going to use the property of exponential to bring this 100 here to an exponent here. So we're going to have e raised to ln of 0.91 raised to 100. So it's usually the inverse that we do. We usually have an exponent and we use the property of logarithms to take out the exponent. Now we have a product and we're transforming this into an exponent. Because E and ln are inverse functions of each other, m of 100 is going to be the initial mass times 0.91 raised to 100. And to solve this, we would need a calculator and we would find 0.00008, which is exactly the answer. So the percentage of the original mass is going to be 0.008% of the initial amount. The last example of application of differentiation that we are going to see today is Newton's law of cooling, which states that the rate of change of the temperature of an object is proportional to the difference in temperature between the object and its environment. So in our problems, we are always going to assume that the temperature of the environment is constant. And so we have um, T, capital T representing the temperature of the object, TE being the temperature of the environment. And then because the rate of change of the temperature is proportional to the difference between those two temperatures, being proportional means, as we have seen, that it's multiplied by a constant K. So it's gonna be K times this difference between the temperatures. So keep in mind that capital T in the problems that we are going to see represents the temperature and little t represents the time. So on the left, we have the rate with which the temperature changes over time. So we are always going to assume that the temperature of the um, environment is constant. And we are going to see that this differential equation is very similar to the differential equation models that we were using before. So what we're going to do is, other than assuming that the temperature of the environment is equal to a constant, we're going to set y equals t minus t. So y of t is going to be the temperature of the object at a time t minus the temperature of the environment, which we are going to assume that is constant. So we can differentiate both sides of this equation with respect to t, and we're going to have d dt of y is equal to d dt of t minus te. So this implies that on the left-hand side, we have dy dt. On the right-hand side, we are going to have d dt, dt dt um, minus 0. So we can replace d dt in this dt dt, sorry, in this expression by dy dt. K is going to remain the same. And t minus t, we just called y of t, so it's going to be replaced by y. So we do know how to solve this type of differential equation. So remember that in the problems that we were seeing, we had dp dt was equal to k times p, where p was the population. And then we saw that the solution to this differential equation was p of t equals p0, the initial population, times e raised to k times t. So we do know how to solve this type of differential equation. And we also know, as a consequence, how to solve this type of differential equation. So the solution to this type of differential equation is going to be y of t equals y 0 or y of 0 times e raised to k times t. Let's consider this last example, which states the following. A carrot cake is done when the temperature of the cake is 200 degrees Fahrenheit, and the cake batter begins at a temperature of 60 degrees Fahrenheit, and the oven is preheated to a temperature of 350 degrees Fahrenheit. So if you take the cake out of the oven and measure the temperature of 150 degrees Fahrenheit half an hour after putting the cake into the oven, then how much longer will you have to wait for the cake to finish cooking? So the model that we are seeing states that the variation in temperature over time is proportional to the difference between the temperature of the object and the temperature of the environment. And then we call y equals t minus te, and assume that the temperature of the environment is going to be constant. And we make a replacement, and we can say that this original differential equation can be replaced by dy dt is equal to k times y. And we know that the solution to this type of differential equation is equal to y of t is equal to y0 times e raised to k times t. So we have to find y of 0 and we have to find k to plug into the solution to this differential equation. So let's see some information that we have about this problem. So first, the temperature of the environment, we are going to consider it to be 350 because that's the temperature of the oven where the cake is going to be put. So the initial temperature of the batter is T of 0, that is equal to 60 degrees. So let's see. Y of T is equal to the temperature of the object at time T minus T of the environment. So in particular, Y of 0 is going to be T of 0 minus T of E. So Y of 0 is going to be 60 minus 350. That is equal to minus 290 um, degrees. So we can replace y0 by minus 290 in this expression. And this is what we are going to get. Y equals y of 0 um, times z raised to kt is equal to that. Now we need to find k to give the equation of the solution to the problem. So to give k, we are first going to consider that y of t is equal to minus 290 times e raised to kt. And we're also going to consider the information that you take the cake out of the oven half an hour after putting the cake in the oven, and you measure the temperature of 150 degrees Fahrenheit. So this means that the temperature at 30 minutes, that is equal to 150. And we do know a relationship between y and t. So y is equal to T minus T, where T is the temperature of the environment or of the oven in this case. So Y of 30 is gonna be T of 30, so 150 minus 350. That is equal to minus 200. So you're going to combine this information with this one. So Y of 30 is equal to minus 200. So this gives us minus 200 equals minus 290 times e raised to k times t in this case is 30, so 30k. We are going to divide both sides by 10, and we're gonna get e raised to 30k is equal to 20 over 29. So taking ln on both sides, we're gonna get 30k is equal to ln of 20 over 29. So k is going to be 1 over 30 times ln of 20 over 29. Now we can replace the value of k in this expression. So once again, that's why we have the value of k. And we can replace this into the expression. So we're going to have y of t is equal to minus 290 times e raised to 1 over 30 ln of 20 over 29 times t. Now we're going to use the information that the cake is ready when the temperature is 200 degrees. So T of T has to be 200 for the cake to be ready. Let's see what it means in terms of Y. So Y is equal to T minus TE. So Y of T is going to be T of T, so 200 minus 350. So we have to find the value of T, of little t, the time, for which Y is equal to minus 150. So now we combine this information with this one, those two equations, and then we get minus 150 is equal to minus 290 times e raised to that exponent. 1 over 30 ln of 20 over 29 times t. Now we can divide both sides by 10. So we're going to have e raised to 1 over 30 ln of that times t, that is equal to 15 over 29. So taking ln on both sides, it's going to give us 1 over 30 times that, 20, 29 times t, that is equal to ln of 15 over 29. So finally, t is going to be ln of 15 over 29 divided by ln of 20 over 29 times 30. And at this point, you would need a calculator to find that this is approximately 53.2 minutes. And because you looked the temperature of the cake at 30 minutes, so half an hour, and because it takes 53 minutes for the cake to be ready, you're gonna have to wait 53 minus 30. So you're gonna have to wait about 23 minutes for the cake to be ready. That was the last example for today. And I'll see you guys next time.